Okay. So thank you very much for having me today, for the invitation. It's my pleasure to be speaking about this work that I did during my PhD under the supervision of Professor Jesse Reed and Professor Albert Biffet from École Polytechnique and the University of Waikato. So today we'll be talking about this algorithm we devised called branches to seek optimal sparse decision trees uh, in an AO star fashion. And I will explain what AO star entails as an algorithm. So first thing is uh, what is a decision tree and why are we interested in such models? So a decision tree is a hierarchical model that partitions the input space sequentially. And then with very easy and simple conditions, like here, for example. And then each partition of the input space each partition is labeled with a class if we are interested in a classification problem. So this property makes decision trees very easy to interpret. And this is an essential property to have in sensitive domains such as the judiciary system, for example, or healthcare. So here I just represented two types of decision tree. The first type is called orthogonal, where you split with respect to just one feature. Another one is the oblique types of decision trees, where you do something like a condition with a linear combination of features. We will be mostly interested in the first type because it is more interpretable. So, albeit decision trees are interpretable by structure, this interpretability weakens as the number of splits, so the complexity of the decision tree grows. So the main motivation now is to seek a decision tree that maximizes accuracy while also minimizing this number of splits, a measure of complexity. Now, unfortunately, such problem is broad and NP hard. So it is very hard to just brute force it. And this is what led to the historical popularity of greedy methods such as CART and C4.5. But the problem is that relying on greedy methods comes at the cost of sacrificing optimality guarantees. And sometimes they can also induce overly complex and deep decision trees. So how shall we go about solving this problem? We noticed that it can be framed naturally into an and/or graph search framework. And then we solve the problem within this framework with an algorithm we call branches, which is an instantiation of AO star, where we define an admissible heuristic that is suited for this decision tree optimization problem. I will explain all of these terms when the time comes. And the results that we would expect, that you will expect in this presentation, are this branches algorithm is guaranteed to be optimal. When I explain what optimality means specifically here, when it terminates. And also, I will provide an upper bound on the total number of branch evaluations before this termination condition. And this is an algorithmic complexity guarantee. And then we compare it with state-of-the-art algorithms such as Ghost on many datasets publicly available from the UCI repository. And we will show that branches always terminates in significantly fewer iterations and often faster. Not always, but often. And also I will explain this anytime behavior, and I would show that branches exhibits a better anytime behavior than Ghost. This is purely empirical, as there is no real theoretical guarantee behind it. So before we get to the branches algorithm, I will first formulate the problem. So I will go over a few definitions. We will consider a classification problem. So we have K classes with only categorical variables. So if you have a continuous variable, you should first discretize it. This is common to do in this decision tree literature. And even most often in the literature considers just binary features. But here we will stay broad. Any number of categories per feature is valid. So the XY follow a joint probability distribution, and we have a fixed data set of IID samples from this joint distribution. Now I will go over a few definitions that are essential to this work. So what is a branch? A branch is just a conjunction of clauses, and all of our clauses are of this type. So it's just a feature equal some category, and this is just an AND operator. And SL, so the number of these clauses is called the number of splits, because these clauses are actually just splits, and so we can call them splits as well. For any input x, we have the valuation L of x is equal to 1 just if this expression is valid for x. So for example, if the branch is x1 is equal to 0 and x2 is equal to 0, then it will evaluate to 1 if x has its first feature and second feature equal to 0. And by convention, the branch that has no clauses at all evaluates to 1 for all data. And so it has a number of splits that is equal to 0. And for all x, it evaluates to 1. In a few slides, I will show a visualization of all of these concepts. Now I'm just laying them down, and then I will be more, I will visualize them more. So for each, if you take a branch, we define the majority class in that branch is the class that we see the most from the data set. So if we have a data set, and we have inputs x that for which L evaluates to 1, and for each one of these inputs we have a class. So the class we see the most is the majority class. And then so the empirical probability is HL that L of x is equal to 1 and K star L is equal to y, which means that x is, we can say, contained in branch L and is well classified, is just this fraction. Then we have also the notion of branch splitting. If we have a branch L, then we can split that branch with respect to some feature I, which yields these children L1, LC until LCI, where each LJ is just L with the additional AND operator and clause xi. So we split with respect to feature I equals j. Okay. And then we have also this notion of a sub dt rooted in a branch L. So if you have a branch L, a sub dt rooted in L is just a collection of branches that stem from successive splits starting from L. And the number of splits we do until getting T is called S of T. We denote it S of T. And so these L1 until LT are a partition of L. So any X that is in L is actually will be contained in one and only one LU, branch LU in T. So the prediction of T for that X is the prediction of that branch. Okay. And so because of that partition property, H of T, which is the probability that X is contained in L and that T predicts X well, is just equal to the sum of these HLU over all the branches of the sub dt. So here is the visualization. For example, you have a branch. This branch is just x3 is equal to 1 and x1 is equal to 0. Okay. So if we take this branch and we split it with respect to some feature x5, and let's say that x5 is binary, then we will have this branch L1 and then branch L2. Then if we further split L2 with respect to feature x2, for example, we will have these two children. And this perimeter, this red perimeter is a sub DT rooted in L that has these collection of branches L1, L3, and L4. Uh, Please feel free to interrupt me if there is anything unclear. Okay? So, and we call a decision tree just a sub DT that is rooted in the root omega. And we recall that omega is the branch, the empty branch that evaluates to 1 for everything. So if we take a decision tree T and we evaluate H at T, because omega evaluates to 1 for every single input, then this H of T becomes just the accuracy. But now the accuracy is not our only object. It's not our objective function, because I remind you that we also want a measure of interpretability. So we will seek to maximize H of T, this accuracy, while simultaneously minimizing the number of splits. So for this, we will optimize this objective function where the accuracy is penalized softly, where we penalize the number of splits. Okay, so for each lambda, we will have some different solution, and if we navigate through lambda, we are essentially building a Pareto front. One very important property of these solutions is that for any lambda, whenever you have some solution T, then we are certain that there is no other decision tree that is less complex. So it has a number of splits that is lower and also more accurate. Okay. So now, how shall we go about solving this problem? How shall we go about finding this decision tree T star that maximizes H lambda of T? We will frame this problem within this and/or search framework. So here, we need to define first a state space model. So our states are just our state space is the set of all possible branches. Also, for each state L, we assign a terminal state L bar. Okay. We have two types of actions. There is the terminal action A bar that just transitions any state L to a terminal state L bar, and a split action that transitions L to the children that stem from splitting L with respect to I. Okay, I will give an example in a second. For our reward model is as follows: any split action in any state, any split action yields a minus lambda reward, and the terminal action yields H of L. This probability that X is in L. X is in L just is another way to write L of X is equal to 1. And that the K star of Lx, so the majority class in L, so X is well predicted by L. And there is also this important notion of a policy, which is just a function that maps states to actions. Okay, so let's look at this a bit visually. We have a state, which is just a branch, L. So if we take the action, the split action with respect to feature X3, we are essentially creating two states. States where we add X3 is equal to 0, and state where we add X3 is equal to 1. We have here just two children because because X3 is binary. If we had the X3, if it had, for example, 5 categories, then we would have 5 children, 5 different children. And we will represent this transition as a hypergraph as follows. In this hypergraph, each node is a state, and each action is represented by a connector that connects the state to the children states that stem from taking that action. For example, here, taking a split action x3 yields 2 children. We have this connector that represents split action 3, and it yields L1 and L2, these 2 children. So let's now take an example, a small example of a full AND/OR graph. This type of hypergraph is called an AND/OR graph. And we get the following. So what do we have here? I have 3 binary features, okay? So I have 4 types of actions. There is the terminal action, and then there are 3 actions, each one for each split action. And each split action corresponds to splitting with respect to a feature. So because we have 3 features, I have 3 actions, 3 split actions. So I denote the terminal action with this loop type of arrow because it just transitions to the terminal state. And for the others, we have a connector that, for example, because all of these are binary, if you take split action with respect to x1 in omega, you will get these 2 children that I represent like this, this just means x1 is equal to 0 and x1 here is equal to 1. Okay? Another important thing to notice is that different branches, so different states, we can get to different states from through different paths. So for example, this state x1 is equal to 0 and x2 is equal to 0. You can get it either by moving to x1 is equal to 0, then x2 is equal to 0, or by moving to x2 is equal to 0 and then x1 is equal to 0. So this is just this is important actually from an implementation standpoint, because branches are they are invariant by permutation of their clauses. So when you can represent many there are different branches that are actually equivalent. They are exactly the same because they are the same. They have the exact same clauses. And if you don't take this into account in implementation, you will end up having more memory and less efficiency also computationally. Okay. And now let's take a look at this example of a policy where at omega, we take split action 1. So you take split action 1, you end up in 2 states. Okay. For this state, we still take a split action 1. For this state, we still take split action 1. So this is by definition. And then we only take terminal actions. So if you notice something here, actually, whenever you define a policy and you follow it from omega, you are actually building a decision tree. So this is actually a decision tree. Okay. Now onto this notion of the value of a policy. We have a policy and we want to evaluate it. So the value of a policy pi at a state L is equal to just the sum of rewards that we obtain by following pi, starting from L. Okay, so in our graph, it would be just the sum of rewards of these connectors, of all of these red connectors. Okay, but it's like we strayed a little bit away. I was talking in the beginning about decision trees, and then I was talking about these AND/OR graphs, but what is the link between them? So there is actually a relationship between this value function v pi L and the objective function h lambda of t, and I will lay this down here. So imagine you have a branch, a sub dt TPL. So you have a policy pi. You follow that policy from branch L. You are essentially building a sub dt that is rooted in L. Okay. So there, V pi L is exactly equal to H lambda of T pi L. And in particular, if you evaluate a policy from omega, so V pi omega will be equal to H lambda of the decision tree that you build from omega by following pi. So now the optimal policy with respect to the value at omega essentially yields the optimal decision tree that we are looking for. So there is an equivalence between seeking that T star, the optimal decision tree with respect to H lambda, and seeking pi star, the optimal policy with respect to the value evaluated at omega. Once you have pi star, just unroll it, just follow it from omega, and you get T star. So now we need the algorithm. In and/or graphs, in these types of graphs, there is this algorithm that was devised in the 70s called AO star, which is a heuristic best first search type of method. It is actually a general, you might have noticed the similarity of in the naming with A star. It's because it's a generalization of A star to and/or graphs. A star is a particular case where you have this algorithm for, they are called OR graphs, or it's not a hypergraph. Okay? And the optimality of this AO star highly depends on the chosen heuristic. And I will explain shortly what I mean by heuristic. This here, I will actually define this heuristic with two functions that are related by the Bellman equation. And if you have a background in reinforcement learning, these might seem very familiar to you. This VL is essentially an analog of the value, the state value function, and QLA is an analog of the state action value function. Okay. So how are these related with this Bellman equation? Instead of giving just the abstract formula, update formula, let's look at it intuitively from this graph. So imagine you have this state L. You have all of these. These are the connectors that stem from state L, and these are its children. Okay. So imagine you have the values. Let's say we have the values of these children, so L1 and L2. Now, what is the value, let's say, of taking action A1 in state L? So it would be, first, we said that the value is the sum of rewards. So first, since we are taking action A1, we incur, which is a split action, we incur minus lambda reward. Then we need to sum up the value of L1 and the value of L2. So the values of all the children stemming from that action. Okay. This is for split actions, but for the terminal action, this value is readily available from the data. It's just equal to HL, which is the probability of landing in L and of correctly predicting X at L. But once you have these Q values for each action, how do you deduce the value of L? Well, the value of L is just equal to the maximum of these QLA. Okay, so these are just abstract heuristics that we need to define and follow in the algorithm in order to get the optimal decision tree. I will show how to do that. So we need a way of initializing these values at these tip nodes, because once you have these VLIs, you can have the Q values, and then you can have the V values for the ancestor nodes. So how to initialize these? Well, In order to guarantee optimality, there is this notion called admissibility in heuristic search literature, which essentially means that your heuristic needs to be an upper bound on the optimal value that we are seeking. So we are seeking the optimal value, which is the value of the optimal policy at L. So we need to define a heuristic, VL, that is an upper bound on it. And here we define this bound called, which we call the purification bound. Essentially what it means, it is the maximum of HL and of minus lambda plus this probability. It is very intuitive. It means that if we are in a state, what's the best we can do? We can either take the terminal action and get this reward, or if we take any split action, the best we can have is minus lambda, this we incur it, and then the best we can have, this is an upper bound on that reward. This actually you only get this is if you purify the children that you get, meaning that the children that you get have only one class in them, hence the naming purification bound. And this heuristic is admissible. So now I will go over a few iterations of the algorithm so that we get the mechanics, the dynamics behind it. In the beginning, we initialize the graph, the and/or graph, with just the root. That's the only thing we have. At the first iteration, we run selection. We need to select which node to explore next. We only have the omega, the root, so we select omega. Next, we expand it, meaning that we create all its children and all of its connectors. Okay, according to the split actions that we have. And once we do that, we initialize VL, these heuristics, at these tip nodes. Okay. Now, once we have this initialization, we can run backpropagation. By backpropagation, I mean you take the VL values that we initialized here, and you use them to update upwards, to update the Q values of the connectors and the V values of the ancestor nodes. That's what you do. So let's run a second iteration. Well, what happens now in the second iteration? So now in the second iteration, at the beginning of the second iteration, we have this graph that we constructed in the first iteration. We need to select where to look next. We select the connector that maximizes the Q values. We want the action with the maximum value. Okay, let's say it's this one. Now we have two states. Which one do we select? Actually, here, whatever one you select, you will get the same optimality guarantee. And also, it is difficult to know exactly theoretically which one is the best, because we have so many degrees of freedom. You can always find the counterexample. There are no smoothness assumptions like when you have Lipschitz functions, for example. So, but a good rule of thumb that I found is to just choose the child that has the current worst solution, so that either so that you can prune that whole region of the and/or graph sooner. Okay, let's say we go through this one. Now we run expansion again. So we have these actions to expand. Okay, we initialize again the values here, and we run backpropagation, and so on and so forth. Now, let's say, for example, that in this node, when we evaluated the value of this terminal action, which we actually know from the data, it's not just an upper bound. We found that it is better than the values of all of these connectors. So the terminal action is better. Then we know that here the best thing we can do is to just terminate, because we have a value, a true value that is higher than upper bounds on the true values. And then we would call this node solved. Okay. Then you backpropagate this notion of solved by, so for example, this node would be solved if all of its uh, children are solved, actually connectors are solved. So branches, this algorithm will continue until omega, the root itself, is solved. Once we get that, once we get that, that selection policy I was talking about of following the connector with maximum Q value actually leads to the optimal. It's the optimal policy. It is the one that we are looking for, and it suffices to then follow this selection policy to get T star. I also devise a complexity guarantee in terms of the number of branch evaluations that you can perform, that you a sufficient guarantee that you on the number of evaluations that branches performs before getting to this optimality guarantee. So, for example, if you have Q features and for each feature you have C categories and you have this lambda parameter, then this number of evaluation is lower than this formula. And so I know this is hard to interpret. It's not like, for example, when you have O of logarithmic functions. So that's why in the paper, what I did was to just evaluate this numerically and compare it with the only other bound that I am aware of from the literature, which was in the OSDT paper, and I showed that this bound is quite tighter. Now onto I will just show some of the empirical results that we have. So here I will compare with in this experiment, I compare with algorithms from the literature that have the same optimality guarantee. So Murtry, Street, Ghost, and branches all essentially, when they terminate, we are sure that what they return is the optimal solution. Now, there is just a little problem with Murtry, I think, in the implementation, because sometimes it does terminate, because this isn't timeout. TO is what I mean by timeout. Yet it has, so let's say, for example, this here. So this is not timeout, yet the objective is smaller than Ghost. And if you look at branches and Ghost and Street also, whenever they terminate, they will have exactly the same objective. If you don't have timeout here, they will have exactly the same objective. Okay, it's also a nice way to debug any problems with the algorithms. So Street and Murtry are depth first search types of algorithms. Ghost is a best first search type of algorithm, and branches is also of type best first search, but with but it is an instantiation of AO star. It does things a little differently. And we will see that if one main difference, a main advantage of best first search algorithms is that they do not need a maximum depth parameter, but for depth first search for DFS, they need it. On the flip side, ghosts and branches can be more memory consuming than Street and Murtry. So this is why, in order to do the comparison, I needed to specify a maximum depth for Street and Murtry. But ghosts and branches essentially run on infinite depth. I chose one that is big, just so that whenever there is a solution, there is a higher chance that the solution is of lower depth. And we will see that we see here that DFS algorithms actually really suffer for high depths. There are other experiments I do with lower depths where DFS can be actually faster. So the important comparison here is mainly between ghosts and branches. And we can see that the number of iterations for branches, which is a loop where to look next and backpropagate. Ghost also has one that is quite different, but this is essentially what an iteration means. And we can see that branches terminates in much fewer iterations. Uh, okay, and also faster on many times. I think there are a few where, yeah, for example, here, Ghost does actually beat branches in terms of time, even though not in terms of the number of iterations. Uh, okay. Another thing that is important here to notice is what I call the anytime property. It's called in the literature the anytime property, which is, so I said that for these algorithms, whenever they terminate, they give exactly the same solution, or exactly solutions that are equivalent in terms of the objective. But what happens if they don't terminate? If if they hit timeout? So you can still use that selection policy to provide the solution. So, and how do these solutions compare? We can see here, for example, I compare the timeout is 5 minutes for all of them. For branches and ghosts, whenever we have timeout, actually I have a branches has a better objective than the one that ghost has. We can see it there. We can see it here also. The objective is better. So these are essentially the important things to notice. Um, Then, after this experiment, another one that I wanted to emphasize is there are these other types of algorithms in the optimal decision tree literature that do not optimize that objective with the soft penalty. They actually optimize a hard penalty. For example, a maximum depth, but they do not actually seek to minimize that maximum depth. DL 8.5 is a very popular algorithm of this type. So in this experiment, what I do is for DL 8.5, I fix the maximum depth to the optimal one that is found by branches, and then I run DL 8.5 for different types of this hyperparameter called the minimum support size for DL 8.5. And I see whether DL 8.5 actually, if we tune it very well, can it achieve the same type of optimal solutions as branches and the other algorithms. And we can see essentially here, this is the objective, that it seldom that seldom happens. So there is no actual guarantee that just tuning DL 8.5 with respect to the maximum depth and the minimum support size will lead you to the same types of solutions that algorithms like branches, ghost, street, and Murtry find. And this is just another way of looking at it, where I have, so in the abscissa, I have the number of splits, and I have here the accuracy. So the more you are to the left, the better, because it means that you get to, for example, here in Monk 3, we get to 100% accuracy in a very low number of splits. And I do the same type of tuning for DL 8.5 again, and I see where it lands. And you can see in many experiments, practically all, that branches, the solution found by branches lies outside of this front that is described by DL 8.5, meaning that DL 8.5 has a hard time finding these types of quality solutions. Um, so that's it for my presentation. Thank you very much for your attention, and please feel free to ask me any questions. I think especially in the visual stuff, there might be a lot of because it's a little bit hard to explain in hypergraphs, especially visually, but please feel free to ask me anything. Thank you very much.